Okay, so we are going to look at logarithmic graphs today in this lesson. However, we're going to do a little bit of review on some earlier concepts when it comes to converting to exponential to logarithmic form as well as log laws. So press pause, try these 3 questions, and then you can press play and watch the explanation. Okay, so for number 4, numeric response 4, it says if log AB equals 1.26, then what is the value of log A cube root B? So the first thing I would do is I would look at this and ask myself, is there a way that I can use log laws to make this look like this? Because they're really close, it's just that cube root is in the way. So with logarithms and exponents, a lot of times you'll be rewriting expressions. So in this case, I'm going to rewrite this argument, and instead of having a radical, I'm going to rewrite as a fractional exponent. Now that I have that fractional exponent here, I can use my log laws. So notice how that exponent only applies to the argument, which means I can move it to the coefficient. So this is now the same thing. Now, because this looks exactly the same and I have the same expression now, I can substitute 1.26 in for that log AB. So really, I'm just taking 1/3 and timesing it to 1.26. And I can type that in my calculator, round to the nearest hundredth, and I should end up with an answer of 0.42. All right, it says if log 2/3 equals A and log 2/10 equals B, then an expression for log 290 is, we talked about this the last lesson at the end, and how when you have something like this, you have to be able to break it up. So not only do we use log laws to bring logarithmic expressions and arguments together, we also can use them to break an argument up. So in this case, I'm going to break this up so that it looks like these. So then I can substitute the A and the B in. So I know 3 times 3 is 9, times 10 is 90. So then this is the same thing, right? All I've done is broke that 90 up into 3 times 3 times 10. With my log laws, I know that I can write this as an expression where I'm adding each logarithm as long as I'm using the same base, which is 2. So now that I've done this, I can just substitute the variables in. So log 2/3 is the same as A plus B. So I end up with an answer of 2A plus B. All right, so then my answer is B. Next question. 2 students were asked to simplify the expression 2 log x plus log x to the third. Their work is shown below. And we're trying to figure out where did they make a mistake. Okay, so a lot of times when I'm working with these types of questions where it asks where did they make a mistake, I'll just go ahead and simplify it by myself without looking at the student's work, and then I'll compare. So I'm going to move that 2 as an exponent on the argument x here. And then from here I'm going to use my logarithm. So I'm going to end up multiplying these 2 arguments. So I'm going to multiply x squared by x to the third. So a lot of these questions, you end up using exponent laws as well. So if you remember, when you multiply 2 exponents with the same base, you add the exponent. So we end up with an argument of x to the 5th, still raised to the power to the exponent of 3. So from here, okay, this is as far as I can go, as I can't bring the 3 in front. The reason I can't do that is because that 3 doesn't apply just to the argument, it applies to the entire expression. I also can't just multiply it into the 5 there because, again, it doesn't apply just to the argument, it applies to the whole expression. So really, this means the same as this. It means log x to the 5th times log x to the 5th times log x to the 5th. And if you were to look at your log laws, there's actually no way to simplify this. This is as simple as you get. So from here, though, it's really easy to find where the students made a mistake. So student A made a mistake in step 3, right? Because they multiplied that 5 and 3 together, which again, we can't do because the 3 applies to the entire expression, not just the argument. Student B, it looks like student B made a mistake right in step 1 there. Okay, because once again, they tried to multiply the 3 in, and really you would have to distribute the whole expression out, right? You can't just multiply the 3 in. You may have known, right, when you did Math 20-1, sometimes I had students do this. This is not the same thing, right? Same with logarithms. You can't just apply the 2 to both terms. You actually have to distribute both of those binomials together. You can't just put a 2 in for each term. Okay, so then that means 7, my answer would be C. So now with log graphs, we looked at exponential graphs a few lessons ago. We talked about how exponential graphs had horizontal asymptotes. So if you remember, exponential graphs, one of the key concepts was that they have horizontal asymptotes. And this, of course, will affect the range of the graph. Logarithmic graphs have vertical asymptotes. So it's almost like they're opposite. Vertical asymptotes, and this will affect the domain of your graphs. So you could try typing these in your calculator, and you would see that you end up with a vertical asymptote of y = 0, no matter what your base is. Okay, so we're going to start just by graphing. So go ahead and try typing this in your calculator. Okay, you should end up with a graph that looks something like this, with that vertical asymptote. Okay, so a lot of times when you type this in your calculator, you'll end up with a graph that looks like this. This happens to kids all the time. And then they'll say, well, the graph stops. Okay, so then that means that the range is not y is equivalent to any real number. Okay, but what ends up happening on your calculator is that this line goes so close to that y-axis that it doesn't actually show up on your calculator. So it looks like it stops, but it actually does continue towards infinity, towards that y-axis. So even though your calculator doesn't show it, okay, with logarithmic graphs, there is a vertical asymptote, and your range will be y as an element of all real numbers, because that line does continue forever downwards in this particular graph. Okay, so just like with exponential graphs, we will talk about transformations and how they apply to logarithmic graphs. So we're going to just talk about some transformations. Press pause on the video, see if you can figure them out, then press play and see if you did them correctly. So this is the original graph, this is the transformed graph. What changed? Notice how the 2's in front. That means you were multiplying this expression by 2. So that means that I'm going to have a vertical stretch, right? That would be my A value when you think back to transformations. So I have a vertical stretch, and we would say by a factor of 2. Along the x-axis. Okay, so if I had a graph that looked like this is my log graph. Ew. Remember, with vertical stretches, you're always going to have an invariant point at the x-intercept there. So your graph might look at something like this if I vertically stretch it. However, that x-intercept wouldn't change because it's an invariant point, and also that vertical asymptote would not change, right? It would still stay at 0 because it's still approaching 0 towards infinity. Okay, so now for this next question, the x minus 2's in brackets. So we're replacing the x with x minus 2. So that means we have a horizontal translation. So we're translating 2 units right. Okay, and you could try to graph this as well. So if you were to graph this, and I'll draw the original again, my new graph would look like this. So I would take that graph, okay, and everything would be translated 2 units right. The x-intercept, all my points, including that vertical asymptote. So now my vertical asymptote would be at x equals 2. So my vertical asymptote would be at x equals 2 now. Okay. All right, next question. It says log 3x minus 2. So this would be a translation, vertical translation. So it would translate 2 units down. Right? And the key difference here is the last question we did, you were replacing the x with x minus 2. That's why it's a horizontal translation. Here, you're kind of just tacking it on into the end of the expression. So it ends up being that k value that we talked about in the first unit. So it's a vertical translation. Okay, because it translates your whole graph, your graph would look like this. If this is my original graph, all that would happen is that it would move 2 units down. So that means, you know, my x-intercept would change. My graph, all those points would move 2 units down. However, that vertical asymptote would still stay at x equals 0. Okay, so now we're going to just compare the two types of logarithmic graphs here, the transformations. Again, I suggest you press pause and then see if you can figure out the question. Okay, so we've always talked about how when you have a b value, which we have in this case, you always want to factor that b value out before you do anything else. Okay, so now that I have that b value factored out, I know this is my a value because it's in front of the expression. So that means I have a vertical stretch of 2 along the x-axis. That b value, remember, is your horizontal stretch, and you're always going to take the reciprocal, so it'd be of 1 over 2 along the y-axis. Okay, and then because I'm replacing the x with x minus 4, that just means I'm going to move this graph 4 units right. Oh, apparently I don't know how to spell units. There we go. All right, and those would be my transformations. So in this case, my vertical asymptote would change because I'm moving to the right. So instead of being at x equals 0, that vertical asymptote, the new asymptote, would be at x equals positive 4 because it would all shift to the right. All right, here's an old diploma question. See if you can figure it out. It gives us 2 points on the graph. They represent a logarithmic graph, and all we're trying to do is, it doesn't actually say in the question, but we're trying to find the value of k. Sorry about that. We're trying to find k. Oh wait, it does say that, sorry. So we're trying to find the value of k. All right, so what I would do is I would start off with the point that you know. Always start with the point that you know. So I'm going to substitute this in. So when y is 1 over 3, x is 2. So the reason I'm doing this is I want to find that b value. So in order to find that b value, I'm going to convert to exponential form. So I'm going to have b to the exponent of 1/3 equals my argument, which is 2. So now there's different ways you can do this. I would probably raise both sides of the equation to 3. The reason I'm doing that is so that the 1/3 and third cancel out, which gives me b to the 1. 2 to the exponent of 3 is 8. So now I know my b value, so I can work with the point that has the k value, the point I'm trying to find. So when y is 2, k is what I'm trying to find. And we know the b is 8 now, so we're substituting 8 in for b. So to find k, my base is 8, my exponent is 2. So I'm going to type that in my calculator. 8 with an exponent of 2 is 64. Excellent. So many questions in exponents and logs. You have to, every single question, be willing to convert back and forth between exponential and logarithmic form. All right, here's another diploma question. So it says, here they give you a partial graph. To produce the graph of y equals f at x above, the values of a and h in the function must satisfy. So first of all, what I would do is I would graph the original logarithmic graph if you were confused and you didn't know what to start. So this is what my normal logarithmic graph looks like. We've looked at it quite a few times in this lesson, so that would just be log bx. Okay, so now this is my new function. So it says to produce the graph of y equals f at x above, the values of a and h in the function must satisfy. So the first thing I hope you notice is the fact that that vertical asymptote has changed, right? It's moved to the right. So if it's moved to the right, we're going to have x minus h. So this h value is positive. Okay, that's a positive h value, right? Because the minus is in front, that doesn't change. The next thing you should realize is that notice how it's been flipped, right? So it's a vertical reflection. So that goes back to Unit 1. When we have a vertical reflection like that, that means we're going to have a negative a value. So with this type of question, what I'll always do is after I think I figured it out, I will actually substitute numbers in for a and h. So on my calculator, I'm going to try typing -3 log. I'm just going to work with a common logarithm, so I don't have to worry about a b value. X minus 2. So I substitute a -3 and a +2 into that expression. And then I'll just make sure that it matches the graph in the picture. And it should, right? No matter what values you choose to substitute in. So now that I've done that, I know my a value is negative, so my a value has to be less than 0. And I know my h value is positive. I have lots of kids who get stuck on that negative. Don't let that negative in front trick you. So now that I know this, I know my answer should end up being A. Yay, A. A for awesome. Okay, last two diploma style questions. So a student sketched the graph of f at x equals log. So we're just going to draw this. Okay, so student A sketches a logarithmic graph. There we go. Okay, let's use orange. So orange is going to be student A. So we know this graph is going to have a vertical asymptote and -3 because it's going to end up moving left 3 units and down 7. But remember, it moving down 7 doesn't really affect that vertical asymptote. So if I were to draw this graph, it'd look something like this. I know the x-intercept is off, but just kind of work with me. The key that we're looking at is that we know that it has a vertical asymptote at x equals -3. So my vertical asymptote is at x equals -3. So now student B draws an exponential graph. Remember how we talked about how exponential graphs have horizontal asymptotes. So if I draw this exponential graph, we also discussed in that lesson about how vertical translation, so moving up or down, will affect that horizontal asymptote. So it moves 2 units right, but it moves 5 units up. So my exponential graph is going to look something like this. Again, and y-intercept's probably in the right spot, but the key is that it's going to have a horizontal asymptote at y equals 5. So those dashed lines represents those asymptotes. So the intersection is just asking for the ordered pair. So it'd be when x is 3 and y is 5. All right, next question. For the graph of y equals log 3b, 3x plus 12, where b is greater than 1, the domain is. So we're looking for the domain. Again, anything to do with transformations or really anything to do with logs at all, I'm going to factor out a b value when I see a b value there. So I'm factoring that 3 out. Now that it's in factored form, it's easy to spot, and I know that this x plus 4 means we're going to move the vertical asymptote, which is usually, so this is usually what my log graph would look like. But I'm moving 4 units to the left, right? So now my graph's going to look like this. So I have a vertical asymptote then at x equals -4. So then if I have a vertical asymptote at x equals -4, that means my domain would have to be x is greater than -4, where x is an element of all real numbers. Okay, key concepts with logarithmic graphs. Make sure you understand transformations and how they affect the graph, and also definitely make sure you understand that logarithmic graphs have a vertical asymptote. Here's some questions for you to practice.